Can you see it?
Yes, perfect. Hello, everyone. It's a pleasure to introduce today Rachana Bhatawdekar, who is an ESA fellow based in Noordwijk, the Netherlands. Rash is originally an electronics and telecommunications engineer from India. After her undergrad, she did a master's in electrical and computer engineering at the University of Maryland in the United States. She worked then in the IT industry as a software developer for around 5 years in the US, India, and the UK, but changed fields to astronomy to pursue her childhood dream of becoming an astronomer. For that, she went on to do a master's in astronomy and astrophysics at the University of Manchester in the United Kingdom, and then moved on to a PhD at the University of Nottingham, graduating last year. Thank you so much, Rash, for accepting our invitation. You may start when you're ready.
Okay, yes, thanks very much for the wonderful introduction, Anna, and thanks very much for inviting me to give this talk also. It's a pleasure to be presenting some of our latest results here today. And hello to everyone else. Thanks very much for joining. So as Anna said, I was a PhD student at the University of Nottingham before I started working at ESA this year. So major chunk of the work that I'll be talking about today, it was actually done as a part of my PhD thesis at the University of Nottingham with Chris Consolis. He recently started working at Manchester, but in addition to that, I will also be talking about the work that I've been doing in my fellowship at ESA. So as you can see, the title of my talk today is Cosmic Reionization, Whodunnit Tale. So what I want to try and do today is talk about one of the major unanswered questions in extragalactic astronomy, which is what are the very first energetic sources responsible for the reionization of the universe? We don't know what these first sources are, and we also don't know when exactly did they form. So I will also talk about the progress in the field that tries to address this very question, and including, of course, our latest results on the basically on the hunt of these very first luminous sources. So that's basically the plan. But before I go into the details, are you able to see my screen still?
Yes.
I hope so. Yeah, I think I'm facing some network issues, but okay, let's see how this goes. So as I was saying before I go into the details, I thought it would be good to first understand what reionization is and why is it important that we study it. So I think everyone is familiar with this little schematic that shows the evolution of the universe. As you can see here, following the Big Bang 13.8 billion years ago, the universe was hot and fully ionized, so hot that even atoms could not form. But as matter cooled after a few 100,000 years, it condensed to form neutral atoms, predominantly of hydrogen, and the universe became electrically neutral. Then what came next were what is called as the dark ages of the universe, because there was no other source of light. The first stars had not been born yet. And then slowly gravitational collapse of the overdense regions led to the formation of the first stars and the first galaxies. And as these first luminous sources began to shine, the ultraviolet light from them knocked off the electrons from hydrogen atoms, and the intergalactic medium became ionized. And this is the period right over here that we refer to as the Epoch of Reionization. Actually, are you able to see my cursor? Because I keep doing this and I'm not even sure if you're able to.
We are.
Okay, okay, great. So it is thought that this reionization must have started as early as redshift 20. And so basically when the universe was just 200 million years old, and must have ended at around redshift 6 or so. So about 1 billion years after the Big Bang. So if we want to understand reionization, we need to look at the first billion years after the Big Bang. So as you can see clearly reionization is an important phase change in the history of our universe, because that's when the universe changed from a neutral state to an ionized state. But in order to ionize hydrogen and maintain the reionization state of the universe, objects actually need to provide UV photons with a very high energy, energy greater than equal to 13 electron volts. So the obvious question is, what were these first energetic sources responsible for such a dramatic phase change, and when exactly did they form? Now, there are a few sources that have been identified for reionization, and those are like galaxies, quasars, and massive, hot, but very young and short-lived stars called as population 3 stars. But who is it is still a real mystery. And this question can be best addressed with the Hubble Space Telescope, which allows us to view the universe back to within 500 million years of the Big Bang. So if you look at the schematic here, you will see that with the help of a series of observing programs with each generation of HST detectors, we have actually been able to probe the star formation and assembly histories of galaxies through more than 95% of the universe's lifetime, which is pretty amazing. So for example, in 1995, the first deep field observations with the HST's Wide Field and Planetary Camera 2, it revealed thousands of galaxies that were fainter than any seen before, of the order 28 magnitude. And this allowed the detection of a significant number of star-forming galaxies out to redshift 5. Then after this, in 2002, the installation of the advanced cameras for surveys, the ACS on HST, it not only produced the most deepest and most iconic optical image of the sky, the Hubble Ultra Deep Field, but it also allowed us to reach optical depths of approximately 29 magnitude, which was fainter than the original deep field limits. And this actually allowed us to uncover new distant galaxy populations out to redshift 7. But revolution in the field only occurred after the installation of Wide Field Camera 3 on HST in 2009, which was mainly due to its infrared capabilities. It allowed the detection of galaxies at redshift 7 and beyond, up to approximately 30 magnitude. And actually, the progress in the field now is such that there are thousands of sources at redshift greater than 6. But how do we actually find these high redshift galaxies? So just to give a very quick background, in principle, there are several methods to do this. But one of the methods that has proved most effective is the Lyman Break technique, or also called as the dropout technique. And what this method does is that it takes advantage of the fact, sorry, I think my video just turned off. Let me see if I can turn it back on. Okay, that's fine, I guess.
It's okay, it's okay. You can go on without the video. We're seeing your screen very well.
Okay, brilliant. Okay, so yeah, so as I was saying, in principle, there are several methods to do this, but one of the methods that has proved most effective is the Lyman Break technique, or also called as the dropout technique. And what this method does is that it takes advantage of the fact that universe is filled with a large amount of neutral hydrogen, and this hydrogen absorbs light at wavelengths lower than approximately 122 nanometers. And because of this absorption, we see a very distinct break, as you can see here, in the otherwise continuous spectrum of an object. So this particular break is called as Lyman break, and the position of this break allows us to understand how much the light from a source has been redshifted. So for objects with redshift of 0, there will be no change in the wavelength of this break because the wavelength of the light is not stretched. And so it will occur exactly at 122.6 nanometers. But for objects at redshift 7, for example, this break will occur at a much brighter wavelength of approximately 850 nanometers, as you can see here. And so basically, if we obtain images of the sky at a number of different wavelengths, we can look for the sources that disappear or drop out at a specific wavelength. And this allows us to calculate the redshift of a source. So if you look at this bottom panel here, this Redshift 7 galaxy has actually dropped out of the blue Z filter, but you can see it in the much redder J filter. So that's basically how it works. And then I can't advance my slide now. Hold on. Okay, great. And then another method of photometric redshift selection to find high redshift galaxies is the template fitting method. And what this method does is that it derives the redshift by fitting a set of template spectra to the observed photometry. Now, the advantage this has over the traditional color selection method is that it makes use of photometry in all the available bands, including non-detections, to estimate the redshift of a source. And what it is also able to do is that it can take into account the shape of a galaxy spectrum about breaks such as the Lyman break, which is otherwise not possible in a single color method. And so this actually helps secure the uncertainty in the redshift. So that's basically the two main methods. And with these two methods, we have been able to find a large number of high redshift galaxies in the past couple of decades. And with the discovery of this significant number of high redshift galaxies, it became possible to make one of the most basic measurements about a galaxy population, which is its census, its number count. What people are most interested in is in the measurement of galaxy luminosity function and galaxy stellar mass function. Now, the luminosity function is nothing but the number densities of galaxies per magnitude bin, as shown here in this plot on the left, whereas the galaxy stellar mass function is the number densities of galaxies per mass bin, shown here on the right. Now, these are generally fitted by a Schechter function, which is shown by this solid red line here in these plots. And I won't go into the details of its parameterization today, but I want to draw your attention to this best fit Schechter parameter alpha, which basically represents the slope of the faint end. Now, this faint end slope is typically negative, denoting an abundance of faint galaxies. And if you look at the literature, there are actually have been several studies by a number of different teams, and the luminosity function and mass function has been studied extensively at high redshift over the past couple of decades. Here I'm showing the luminosity function studied by Finkelstein et al. At redshift 8. And as you can see, they found a very steep faint end slope at this redshift, which essentially means a significant contribution from the faint galaxies. Then Song et al. Studied the galaxy stellar mass function from redshift 4 to redshift 8. And what they found is that the mass function also evolves with time, and it actually becomes steeper with higher redshift, such that there are more low mass galaxies at high redshift than at low redshift. So what these studies essentially are suggesting is early star forming galaxies could well be the best candidates to drive reionization. But the challenges that these studies are facing is that they have reached their limit around an absolute magnitude of minus 17. Now, why minus 17? Because that's the observational limit of HST, which basically means that Hubble cannot see faint objects beyond an absolute magnitude of minus 17. And previous studies have actually suggested that the contribution from these galaxies detected in the current surveys is not sufficient to match the ionization background that is required to reionize the universe by redshift 6. So basically, in order for this idea of galaxy-powered reionization to actually work, where we think that galaxies could be the most likely candidates to cause reionization, we actually need to observe galaxies that are 100 times fainter than the current observational limits of HST, which essentially means, So this essentially means that we need to integrate the luminosity function to an absolute magnitude of around minus 30. But another problem is that theoretical models predict a turnover in luminosity function at some absolute magnitude greater than minus 17. So should this happen, it will present a challenge for our models of galaxy formation. Now, with JWST, finding these distant faint galaxies will be a routine. But the question is, how can we extend Hubble's reach until then? And this is where we can take advantage of the magnification effect caused by gravitational lensing. And the way this works is that, as you can see in this cartoon here, massive objects such as galaxy clusters bend the space around them in such a way that if there is a source lying behind the cluster, such as this, the light from the source will be magnified. And this will be seen in the form of multiple images of background source strongly distorted into arcs or rings, as you can see here. Now, this gravitational lensing effect can actually result in magnifications up to a factor of 100, allowing us to directly observe the faintest galaxies beyond HST's limit. And so for this reason, the Hubble Frontier Fields program was designed in 2013, which is a director's discretionary time campaign with HST and Spitzer Space Telescope to address the very question of how deep can we go now with HST before the launch of JWST. And to do this, Hubble observed these 6 massive clusters of galaxies as gravitational lenses, along with 6 adjacent parallel blank fields for 840 orbits and spanning a wavelength range of 0.4 to 1.6 microns. So these clusters essentially act as magnifying glasses, allowing us to see those more distant faint galaxies beyond Hubble's reach. And you can actually see this very phenomenon in the form of these beautiful arcs caused by lensing in these images here. And the parallel blank fields are basically just for deep observations. Okay, so as I said, we can take advantage of lensing to find the faint galaxies, but unfortunately, the story doesn't just happily end here. There is a problem, and the problem is that even though these galaxy clusters enable the detection of faint sources by providing a magnified boost to the light from the background galaxies, in practice, detecting these sources is extremely hard. And the reason for this is that these clusters are also home to these massive bright foreground galaxies in the cluster. These galaxies are so massive and so bright that it makes it almost impossible to see the faint objects. And so, so to solve this problem, in my PhD, I developed a technique that gets rid of the massive foreground galaxies in the cluster, allowing for a cleaner and deeper detection of the faintest systems. It's a complex procedure, and unfortunately, I don't have enough time to go into the technical details of it, but it is described in detail in our paper that was published last year, in case you're interested. But basically, it's an iterative process, which I like to call it as divide and conquer, because in this method, what we do is that we divide or split the image into small regions with the target bright galaxy in the center, and then use GalFit on those regions to model the small neighboring galaxies first before trying to model the big galaxies. Now, the reason we do this is because when we tried subtracting just the bright galaxy, it gave us a very bad residual. And we realized that the reason this was happening is because these foreground galaxies in the clusters are not only very bright and massive, but they also lie in a crowded field, meaning that there are also many other galaxies nearby. And basically, so the neighboring galaxies were also contributing light to the so-called stamp of the target bright galaxy. And so if we got rid of them first, it resulted in a better residue. So what we do is that we model the small neighboring galaxies first. And once they are fitted away cleanly, we model the target bright galaxy. So for example, in the top left of this image here, I've shown the target center bright galaxy in orange circle, which we wanted to subtract. And so we subtracted the neighboring galaxies on the top first, the GalFit models of which are shown in this middle panel over here. And on the right is the residual after we subtract the models. So as you can see here, this process revealed 2 faint sources that were hiding behind the foreground galaxies. Then again, in the bottom row left is an image with a smaller system on the top subtracted out, leaving just the central target bright galaxy. Then in the middle is the GalFit model of the central target galaxy, and on the right is the residual image, clearly revealing the faint sources that were hiding behind it. So basically, we do this for all the bright galaxies in the cluster, and this is what we get. So what you are seeing here on the left is MAX 0416 cluster on which the subtraction procedure was applied. In the middle is the models of galaxies that were subtracted from the cluster, and on the right is the final subtracted image. And if you look closely at this image, you will see that some of the faint sources that were hiding behind the bright galaxies are now clearly seen after the subtraction procedure. So, so far so good. We can find the sources hiding behind the foreground galaxies once they're subtracted out. But we also need to know the properties of these sources, like their redshifts and their luminosities and their stellar masses, in order to derive the luminosity function and mass function. And for this, we need a multi-wavelength photometry catalog. And I will just very quickly explain why we need it with this figure that is in front of us. So this is an example of a redshifted SED of a redshift 7 galaxy. You will see several features, several features like absorption lines, the familiar Lyman break, and other breaks such as Balmer break and 4,000 angstrom breaks. Now, the Balmer break, 4,000 angstrom break you're seeing here, this break is particularly crucial to estimate the age of stellar population and subsequently in the measurement of galaxy stellar mass. But if you notice, this break is actually moved beyond 2.4 microns at this redshift, at redshift 7. And because we are interested in sources in the first billion years after the Big Bang that caused reionization, so essentially sources at redshift 6 and beyond, we need to look at wavelengths beyond 2.4 microns. And as you can see here, only the IRAC camera on board Spitzer can identify the break. Now, thankfully, the frontier fields clusters were observed by HST, VLT, and Spitzer Space Telescope, and this allowed us to construct a multi-wavelength photometry catalog, which spanned a wavelength range of 0.4 to 4.5 microns. So 0.4 to 1.6 microns with HST, then K-band from VLT at 2.2 microns. It basically helped fill in the gap between the 1.6 micron and the 3.6 IRAC channel. And the longer wavelength IRAC data at 3.6 and 4.5 microns, it helped us put better constraints on redshift estimates, as well as to obtain robust stellar mass estimates. Then what is also important, because we are dealing with cluster seers, is to have reliable lensing models as they tell us the distribution of matter in the clusters. We basically need them to interpret many of the properties of the background lens galaxies correctly. And for the frontier fields, the lens models were produced by these 7 independent teams for all 6 clusters. Each team uses different methods, assumptions, and software, which I won't go into the details of. On the right, I have shown the lensing model by the CATS team for Able 2744 cluster, just as an example. But in our work, we basically use all these lensing models to calculate the median magnification factor with which we demagnify our stellar masses, luminosities, and star formation rates. And so with our subtraction method combined with lensing, we were able to derive the very first galaxy stellar mass function for frontier fields program. The stellar masses of our high-redshift sample were estimated by CD fitting method using imaging from HST, Spitzer, and VLT. And in these plots, we are showing the number densities of galaxies as a function of their stellar mass at each redshift we study. And the solid green line here in these plots is basically the Schechter function fit to the data. Now, these results were actually published last year, and a key result of this paper was that we were able to characterize the mass function to the lowest measured stellar masses for the very first time with frontier fields, 10 to the 6.8 solar mass. And as you can also see in these plots, our results are showing a steepening of low mass end slope alpha with increasing redshift from minus 1.98 at redshift 6 to minus 2.38 at redshift 9. So these results actually confirm the previous trend found by some studies that as one goes back in time, there are more lower mass systems at earlier times than there are today. But what is different is that these slopes are actually steeper than previous studies. And what this essentially means is that there are a significant number of low mass galaxies in the universe that we were unable to see with Hubble alone, which is pretty exciting. And then using the same sample, we were also able to derive the UV luminosity function from redshift 6 to 9, and we were able to characterize it to magnitudes as faint as minus 13.5, as you can see here in this plot. Now, remember that theoretical models actually predict a turnover at some absolute magnitudes greater than minus 17. And there have been a couple of studies, mainly by Etek et al. And Bhuvan et al., who are finding this turnover at magnitudes around minus 15, shown by these yellow and black points in this plot. But we are finding no evidence of a luminosity function turnover to magnitudes as faint as minus 13.5. So what's the reason for this discrepancy? Now, an important factor that we need to consider here is that when you are deriving luminosity functions and mass function, completeness plays a major factor. So completeness correction helps us better constrain the low mass end of mass function and the faint end of luminosity function. However, an overcorrection can lead to an artificial steepening of slopes. And Bhuvan et al. Have, in their 2017 paper, shown that only the most compact galaxies can be detected in high shear regions, which basically means that extremely faint galaxies at high redshift have near point source-like profiles, resulting in smaller completeness corrections and therefore shallower faint end slopes. And so, considering point-like sources in their completeness simulations, they are basically finding a turnover, as we can see here. So to look into this, we carried out our completeness simulations with two galaxy size distribution, one with the disk-like galaxies and one with point sources. And in these plots, we are showing the Schechter function fit with both these scenarios with this solid green line and this dashed green line. But in both the cases, we are not finding a turnover. And instead, what we are finding is that the faint end slope of our luminosity functions are also exhibiting an apparent steepening with increasing redshift from redshift 6 to redshift 9, similar to our stellar mass functions. Now, there hasn't been a comparison like this in studies after our paper, so this is something that definitely needs to be looked into in detail again. But as of now, we are finding no evidence of a luminosity function or a mass function turnover in our work. And so with these new measurements of luminosity function and mass function, we were also able to estimate the UV luminosity density at each redshift we study, which basically tells us how many UV photons there are per unit volume. And we do this by integrating our luminosity functions to magnitudes of minus 13.5, which is the faintest galaxy in our sample. This is shown by these orange circles here in this plot. And for comparison, I have also shown the luminosity density estimated by integrating it down to magnitudes of minus 17, which is the observational limit of HST. And as you can see, these results with minus 13.5 are quite high compared to minus 17. And again, if you remember, I mentioned at the very beginning of this talk that in order for galaxies to complete reionization by redshift 6, it requires that the universe must be significantly ionized by faint galaxies. And this is exactly what these points are telling us. Then if we look at the plot of stellar mass density as a function of redshift, shown here on the right, which I have estimated by integrating our mass functions, what we find is that the integrated stellar mass density has increased by a factor of 15 from redshift 6 to redshift 9. And what we also see is that there is a surprisingly high amount of stellar mass density for galaxies in the early universe up to redshift 9. So this basically is an indication that galaxies of masses around 10 to the 8 have already formed a significant density by this time. So what this also tells us is that star formation and assembly history for galaxies is significant in the epochs of redshift greater than 9, which we cannot probe in detail until the launch of JWST. But basically, these results do support the idea that faint galaxies in the early universe could have been responsible for the reionization of the universe. And since this seems to be the case, that faint galaxies could be the most likely candidates to cause reionization, we recently also went hunting for population 3 stars in our sample. These POP3 stars are theorized to have been the firstborn stars created in the universe and therefore composed entirely of the pristine gas left over from the Big Bang, that is hydrogen and helium. other heavier elements, which we refer to as metals, like carbon, nitrogen, oxygen, iron, etc. These are actually cooked up inside the cores of these stars. Now, these population 3 stars are extremely hot and massive, and so they are much bluer in color than normal stars. And being very hot and massive, they are also very efficient sources of UV photons, which makes them a leading candidate for reionization. And so to look into this, we looked at the UV colors of our sample of galaxies to see exactly how blue they looked. Now, traditionally, this is done by looking at something called as UV spectral slope beta, such that the UV spectral energy distribution has this form, f lambda proportional to lambda to the power beta. And so if you fit a power law to the spectrum, as shown in this plot here, you would get some slope. If the slope is negative, it means that the galaxy has much more blue light. And if the slope is positive, then that would mean that it has much more red light. And if we look at the literature, there are studies that have reported UV continuum slopes as steep as beta equals -3. And this suggests the presence of exotic stellar populations. And these very steep slopes can actually be explained by extremely metal-poor stars or a top-heavy IMF in these galaxies. Although on the other hand, there are also other works reporting contradictory results with redder values of beta. But regardless of the varying results, the general consensus now is that values of beta equals -2 are typical for even the faintest galaxies detected with HST. But the problem is that the number of such faint sources is still very small, and they only exist at magnitudes less than -17. Now, since with frontier fields, we are able to see more faint galaxies, this can basically offer the very first insights into the UV colors of galaxies in a magnitude range of -17 to -13. And this is particularly exciting because models actually predict that values of beta equals -3 do not appear until magnitudes greater than -17. So basically, should we detect such blue slopes from these galaxies, we will potentially discover the very first evidence for very low metallicity star formation in the early universe. And so to look into this, we looked at the UV colors of our sample of galaxies by looking at UV spectral slope beta. And as I said earlier, previous studies that have looked at UV slopes, the faint sources for them existed at magnitudes less than -17, which is shown by this dashed blue line over here in this plot. So that's basically the limit of those studies. But with frontier fields, we are for the first time able to look at the UV colors of galaxies between -17 and -13. So in these plots, we are first examining if there exists any correlation between rest-frame UV and beta by plotting beta as a function of magnitude from redshift 6 to redshift 9. Now, the black points in these plots represent the median values of beta in three different bins. And as you can see here, we are not finding a correlation between rest-frame UV and beta at all redshifts we study. But what is interesting is when we look at beta as a function of redshift, this is what we find. Now in this figure, we have plotted the median colors of all the galaxies in our sample at each redshift we study with these yellow points. And what we find is that beta appears to evolve from redshift 6 to redshift 9 such that galaxies exhibit bluer values of beta at high redshift. And this blue dotted line over here, it suggests the expected colors if galaxies had stars with very little metals. So what this is telling us is that even though we are finding blue values, these are not blue enough to have stars with very low metallicities. Now, this is the first time that we are able to probe a wide range of magnitudes with frontier fields. And so what these results basically are telling us is that even though we are looking at a very young universe that is just 500 million years old, galaxies have already been enriched by metals of significant amount. This essentially means that star formation predates even this very early redshift, and only JWST will provide a clear picture of this. But as of yet, there is no evidence for POP3 stars at the highest redshift probe with frontier fields. So, in a way, it is sad that Hubble cannot see the first galaxies, but these results clearly show the potential science that can be done with JWST. Um, JWST, which is scheduled for a launch next year, fingers crossed, big time. It is optimized for infrared wavelengths, and it will cover a longer wavelength range from zero point 0.6 to 28 microns. And so it will help us detect the first light objects in the redshift range of 10 to 15. And this will increase the current redshift 10 sample by a factor of at least 2 to 3, and it will add the completely unexplored epoch of redshift 12. As far as my research goes, I'm planning to combine JWST with lensing, which will potentially help me find even fainter galaxies than I'm able to do with HST. With that note, I think I will just summarize my talk by saying that with the help of lensing of massive clusters, we have studied the low mass and slope of mass function, faint of luminosity function, and UV colors at redshift 6 to 9 with frontier fields. With our subtraction method combined with lensing, we have been able to characterize the mass function to the lowest measured stellar masses for the first time with frontier fields. And we have also been able to characterize the luminosity function to magnitudes as faint as minus 13.5. Then we have also observed a steepening of low mass end slope as well as faint end slope with increasing redshifts. But in the same cosmic time interval, we have found a lack of evidence of exotic or POP3 stellar populations. And so these results basically do strongly support the idea that low mass faint galaxies in the early universe could have been responsible for reionization. Finally, these results also also show that galaxies and structure formation predates even this very early redshift and shows the potential science that can be done with JWST, which will look even further back in time and provide a clear picture of the first stars and first galaxies. So thanks very much. Thanks for listening. And I'm happy to take any questions or comments.
Thank you, Rash. Thank you very much for your talk. For the people following the talk on YouTube, thank you for joining us. If you have any questions, please post them on the channel and our speaker will answer them later.